Hello everyone and welcome back to Networks class. Last time in class we discussed a couple of examples of min-cost flow. So we looked at how to use min-cost flow to solve a production planning problem for a large manufacturer. And then we talked about an application of tracking moving objects that appear in consecutive frames of a camera. And the plan for today is to go back and look at a couple of applications of max flow, which are tanker scheduling and network reliability. But of course, all of us should know at this point that max flow is the same thing as min cost flow in many ways. And so even though these are max flow applications, they're also min cost flow applications. Okay, so let's just begin with this tanker scheduling application. So in this application, we're giving the following data. So we have a number of shipments that we want to complete. So for each shipment, we have a shipment number, a from port, a to port, and a deliver on date. So for example, shipment 0 has to go from port A to port C, and we have to drop it off exactly on day 3. Shipment 1 has to also go from port A to port C, and we have to drop it off on day 8. Shipment 2 has to go from port B to port D, and we have to drop it off on day 3. And shipment 3 has to go from port B to port C, and we have to drop it off on day 6. So in addition to these shipment numbers, we also have some travel times. So in particular, a ship moving from one port to another is going to have a different travel time if it's loaded or if it's empty. So the loaded travel times are going to be the following. So we have a from port and a to port. And we could either be coming from A or B and going to either C or D. And the travel times are just 3, 2, 2, and 3. And the empty travel times, again, have a from port and a to port. And we could either be going to A or B and coming from either C or D. And the travel times are 2, 1, and 1 and 2. And so the basic question that we want to ask, given all of this data, is what is the minimum number of ships required to complete all shipments? So for example, we can't have the same ship completing shipment 0 and shipment 2 because both of those shipments have to happen in the same day. But we might be able to maybe have the same ship do shipment 2 or 3. We don't know. But the basic question is we want to use the minimum number of ships for all of these required shipments. So we're going to solve this problem in several steps. So in the first step, what we're going to do is we're going to create a graph out of the shipments. So typically, so far, if I gave you a problem like this, you might think of creating a graph out of the ports. But this time we'll create a graph out of the shipments. So in particular, the nodes are going to be different shipments. And there's going to be an edge from I to J if a ship completing I can also complete J. So let's see how this graph looks. So here we have the different shipments as nodes, 0, 1, 2, and 3. And we're going to put edges if a ship can complete, we're going to put an edge from I to j if a ship completing I can also complete j. So let's see if we're going to put an edge from 0 to 1. So can a ship that completes shipment 0 also complete shipment 1? Well, let's see if that's the case. A ship completing shipment 0 is going to be in port C on day 3, and it's going to be empty. Then, to complete shipment 1, it has to travel from port C to port A empty. So that's going to take 2 days. So that means it's going to be in port A on day 5. And then it has to travel from A to C full, which is going to take 3 days. So that means the earliest it could get to C is on day 8. And that's also when the shipment needs to be delivered. So yes, it's possible that a shipment completing shipment 0 can also complete shipment 1. And that's why we put this edge from 0 to 1. So let's see. Can a ship completing shipment 0 also complete shipment 2? Well, that's not possible because shipment 0 happens on day 3, and so does shipment 2. So no edge from 0 to 2. What about a ship completing shipment 0? Can it complete shipment 3? So let's see. It's going to be in port C on day 3. Then it has to travel from C to B, which takes 1 day. So it'll be on B on day 4. And then it has to go from B to C, which is going to take 2 days when it's loaded, which means it can be at C on day 6. And that's also when the delivery date is. So yes, a ship that completes shipment 0 can also complete shipment 3. So we're going to add that edge from 0 to 3. And similarly, we're going to ask the same question for all pairs. So let's, there's only one other edge that ends up being drawn in here. So let's just do this one last one as an example. Can a ship completing shipment 2 also complete shipment 1? Well, the ship is going to be at D on day 3. Then it has to travel from D to A, which takes 1 day. So it'll be at A at day 4. Then it has to travel from A to C full, which is going to take 3 days. So it could be at C on day 7. And 7 is earlier than 8. So yes, a ship that completes shipment 2 can also do shipment 1. So that's our basic graph out of the shipments. So the next step is to split the shipment nodes. And add a lower bound of 1 on the edge inside the split. So this is what I mean. We're going to take this graph, and each of these nodes will split it into 2 parts. So 0 is going to turn into 0 start and 0 end. 1 is going to turn into 1 start and 1 end. 2 is going to turn into 2 start, 2 end. And same thing for 3. 3 start, 3 end. So I split this node 0 in 2, and I'm going to put an arc from the 0 start to 0 end. And this arc is going to have a lower bound of 1, meaning that I require one ship to actually go from 0 start to 0 end to complete this shipment. So a similar thing for all of these. These are going to have a lower bound of 1. Now, these edges that we had previously that connected 0 to 1, what these actually mean is that a ship that is at the end of shipment 0 can go and complete shipment 1. So that means that arc is going to translate into an arc like this, from 0 end to 1 start. So it means that a ship completing shipment 0 can go to the beginning of shipment 1 and complete that shipment. So similarly, the other 2 arcs go from 2 end to 1 start, and from 0 end to 3 start. So those were just the arcs in our original shipment graph. I just copied them on here. So the final step to create this graph is we're going to add an S and T node. We're going to add edges from S to every start node, and add edges from T to every end node. So let's see how this looks. So we have our graph thus far. And we're going to add to that an S and a T node. And we're going to add these edges from S to the start of every shipment. So what these edges represent is the fact that we could bring a ship into service to complete this shipment. So these edges out of S just represent bringing ships into service. And the edges to T, I'm going to draw them with dashed lines so that they're a bit easier to follow with our eye. Those edges represent the fact that we could take a ship out of service at the end of completing a shipment. So these are just some options for bringing in some extra ships and for taking ships out of service at the end of completing a shipment. So this is the graph that we're going to use to try to compute the minimum number of ships required. And we're going to do this computation of minimum number of ships using the maximum flow problem. But you know that maximum flow sends as much material from S to T as possible. So if we were to just directly apply maximum flow here, we'd be kind of sending way too many ships. We actually want to solve the minimum number of ships that complete all of these 4 deliveries. So we have to do this with a slight change. So we're not going to apply max flow directly. We're going to do a bit of a change on that. So let's see what the change is that. So to solve this problem, we're going to do the following steps. First, we're going to find any feasible flow that satisfies the lower bounds. So we have these lower bounds on the delivery arcs, and we want to find a feasible flow that satisfies them. In general, we could do this with the application that we learned about a couple of lectures ago that lets us find feasible flows on any graph that has lower bounds. But for this particular example, there's a very simple flow that satisfies all of these lower bounds, which is just bring a ship into service for every one of these shipments. So there's going to be one ship that we bring into service to complete shipment 0, and then we're going to take it out of service. One ship that we bring into service for shipment 1, then we'll take it out of service, and so forth. So for this problem, it's just bring a ship into service for every delivery. The problem is that the feasible flow we found could be using too many ships. So our idea of using 4 ships, 1 for each shipment, potentially uses too many ships. And so we want to kind of figure out the minimum number of ships to do all of these shipments. So to do this, what we're going to do is the following. So in the residual graph, for the feasible flow that we found. We're going to push as much flow from T back to S as possible. So we're going to be moving flow from T back to S, and every time we move some flow from T back to S, we're going to be using less and less ships to actually complete all the deliveries. But the problem is that as we're moving this flow from T back to S, we could potentially not be executing the deliveries anymore. So what we have to do is a small adjustment on the residual graph. Except what we're going to do is we're going to reduce the residual capacity on arcs with lower bounds so that we preserve the flow satisfying the lower bound. So let me give an example of what I mean in terms of this reducing the residual capacity change. So suppose we had a graph here that in the original graph had a lower bound of 3 from A to B. In the feasible residual, we had a residual capacity from B back to A of 7. So that means that we're not only moving 3 flow here, we're actually moving 7 flow from A to B for whatever reason. And so we have this residual capacity from B back to A of 7. Now, as we're pushing flow back from T to S, one of the things that might happen is I might move 7 units of flow from B to A. But if I do these 7 units, I'm going to be actually violating the lower bound that I had originally. So to make sure that I don't do that, what I'm going to do is reduce the residual capacity. So before I start moving this flow from T back to S, I'll change this arc so that it looks like this. So that it only has 4 capacity. I reduced it exactly by maintaining these 3 units that are required to satisfy the lower bound. So now, as I move flow from T back to S, I can happily remove all 4 of these units, and everything will still be feasible. So we have to do this kind of residual capacity reduction before we actually start moving flow from T back to S. So let's apply these 2 steps on our tanker scheduling problem to actually figure out what's the minimum number of ships that we can use to complete all of the shipments. So let's go back to and copy this original graph to run the entire algorithm on it. So this is our original graph. Now let's draw the residual graph for the feasible flow that we had in mind. So our feasible flow brought a ship into service for every delivery. So to draw this residual graph, I need to know what the upper bounds on these arcs are. So let's imagine that all upper bounds are 1, meaning that I don't want more than 1 ship on any of these arcs, which for this particular problem makes sense because we're not going to have more than 1 ship, for example, carrying out a particular delivery. So the residual graph of our feasible flow looks like this. We're going to be bringing in a ship into service for each one of these deliveries. So all of these arcs that go from S to the start nodes, they reverse direction in the residual because they now have flow on them. Similar thing for all of these arcs between the start and the end nodes. They're now pointing in the opposite direction because they now have flow on them because there's a ship that's actually doing that delivery. So the ship comes into service, it does the delivery, and then it goes out of service. So these arcs from T that are connecting the end nodes to T, they also reverse direction. So here they are. They reverse direction in our residual graph. So the only arcs that don't have flow in them are these arcs that connected the end nodes and the start nodes, because we're not having any ship right now in our current feasible plan. We're not having any ship that sort of completes one delivery and then goes and does another delivery. We're just having ships that complete the delivery and then go out of service. So that's why these arcs from end to start, they just stay here. And then we also have this one from 0 end to 3 start. So this is our residual graph. So now we have to do the capacity reduction. To maintain the lower bounds. So all of these arcs that are on our graph have a residual capacity of 1. And our original lower bounds were also 1, as you can see up here. So when we do the capacity reduction, what's going to happen is that these arcs pointing from the end nodes back to the start nodes, their capacity actually is going to get reduced to 0. And I'm going to picture that by simply erasing them. And so it's in this graph here that we want to push as much flow from T back to S. So let's do that quickly. So let's identify a route from T to S that we could push flow on. So here's one route from T to 2 end to 1 start to S. So when I move some flow on that route, it's going to edit these arcs. It's going to change their direction. So this arc is going to flip around, this arc is going to flip around, and this one is also going to flip around. So now I have to look for another route from T back to S. So here is one from T to 0 end to 3 start to S. So let's move some flow on that one. And now when I try to find a path from T to S, I won't be able to find one, because the only way to exit T is on this arc, which leads to a dead end, or this arc, which leads to a dead end. So now I've moved as much flow back from T to S as possible. So this is our final residual after we've pushed everything back. So let's copy the original and the final residual to be able to pull out the shipping plan to actually figure out which ships to send where, so that I'm doing all these deliveries with the minimum number of ships. Okay, so in this final residual, we have some arcs here that we had purposefully decreased the capacity to kind of maintain the ship that was doing the delivery. So let me just draw those back in now. because we're done moving flow from T back to S. And now we can take a look at these two graphs to actually pull out a shipping plan. So we can compare the original and final residual to see which arcs have flow, which in turn tells us how we're routing the ships. So let's take a look at this arc from S to 0 start. In the original, it's pointing from S to 0 start. In the final residual, it reversed direction. So that tells us that there must have been one ship that moves along this arc. This ship then has to go and complete this delivery, and you can see that in the original this arc was pointing in this direction. In the final residual it's pointing in the opposite way, which tells us that there's flow right there. Then at 0 end, let's see where the ship goes. Well, this arc is pointing the same way in both graphs, so that means it must not have flow on it. This arc is pointing in opposite directions in the two graphs, so that means that must be where the ship went. And this third option is pointing in the same direction in both graphs, so no flow on it. Okay, so the ship completed delivery 0, and then now it moved to delivery 3. And so it completes delivery 3, and you can see that that edge has some flow on it. And at the end of delivery 3, it goes to T, and you can see that by looking at these two edges. So that's one of the ships that we have. We bring it into service to complete delivery 0, then it completes delivery 3, and it goes off out of service at the end of that. So let's see if we have any other ship. So this arc from S to 3 start, it's pointing the same direction in both, so we didn't bring any ship into service there. The one from S to 1 start is pointing the same way in both, so we didn't bring any ship into service there. But the one from S to 2 start is pointing in different directions, and so that means there must have been a ship that we brought into service for that. So we have one ship, we brought it into service for delivery 2. It then goes and completes delivery 2. At the end of delivery 2, it doesn't go out of service. You can see that by looking at these two edges. But it instead goes and completes delivery 1. You can see that by looking at those two edges. So it completes delivery 1. It completes delivery 1. And then at the end of delivery 1, it goes to T out of service. So we were able to complete all 4 of these deliveries with just 2 ships. So that's the basic idea of this problem. So we were able to solve for the minimum number of ships from S to T using max flow by basically finding a feasible solution, making sure that we maintain the lower bounds, and then moving as much flow from T back to S as possible. So here's some general things to pull out from this problem. So the first general thing to pull out is the fact that we split the shipment nodes in 2. And that's a very general kind of idea. So if I have a node here with some arcs going in and some arcs going out, and I want to put some kind of node capacity on it. So for this problem, we wanted to put some lower bounds that made sure that at least 1 unit of flow was going through the node. But in general, we might also have some upper bounds or other things we want to put. We can do that by taking this graph with just the node in it and splitting the node into 2 nodes, let's say A prime and A double prime. By doing this kind of split, we're making sure that any path that goes through node A has to now go through this arc. And so we can put capacities or lower bounds here, or costs. And these capacities, lower bounds, or costs are kind of like putting capacities, lower bounds, or costs on the node right there. So that's one of the things to learn from here. But let's think about a few twists on this problem. So the first twist is, how would this problem be different if, let's say, delivery 0 required 3 ships, delivery 3 required 2 ships, delivery 2 required 5 ships. We can put in these different requirements by just changing these lower bounds. So right now the lower bounds are 1 because those shipments require just 1 ship to complete. But if I needed 2 ships here, I could just change these lower bound to 2, and all of a sudden it would require me to have 2 ships to actually deliver that. But other than that, the solution method would be exactly the same. Another twist you might think of on this problem is the following. So suppose that I have some big ships and some small ships. How can I solve for the deliveries when, let's say, delivery 0 requires 3 big ships and 2 small ones, delivery 2 requires 5 small ones and 1 big one, and delivery 3 also has some kind of requirement for big and small, maybe 5 big ones and 2 small ones. Well, to do this, you can have just totally different problems for the big ships and the small ships. So I have one graph like this for the small ships, a totally different graph like this for the big ships. I solve for how to route the various ships around, and what's going to happen is I'm going to have the exact number of ships for shipment 0. If I need 3 small ones and 2 big ones, I'm going to have those be there for shipment 0. But at the end of the shipment, that group isn't going to stay together. They're just going to spread out to kind of complete the rest of the shipments based on whatever requirements for big and small ships there are for the rest of the shipments. So you can think of that as a kind of multi-commodity flow where we have a small ship commodity and a big ship commodity. But it's even simpler than a multi-commodity flow because we don't have some kind of common constraints between those. So they're just totally separate constraints for the small ships and the big ships. So let's do a couple of other twists on this. So we saw how to solve this problem with max flow. But it turns out you can solve it with min cost flow as well. So we can solve tanker scheduling with min cost flow just as well. And the idea for this is the following. So let's go back and just copy our original graph here. So this is a copy of our original graph. To solve the tanker scheduling problem with min cost flow, we can do the following. We can have the exact same graph, except I'm going to add a cost of 1 here and a cost of 1. By adding these costs, what we did was we just said that there's a cost of 1 for bringing a ship into service. And we want to find the minimum cost way of satisfying all of the lower bounds that are in the graph. Except if we were to run this right now, it would give us an answer of infeasible because there's no way to satisfy these lower bounds because there's nowhere for the flow to come from. So we need this edge from T back to S. So when we have this edge from T back to S, all the node balance constraints can be satisfied, and we can find the minimum cost flow to find all of the deliveries with the minimum number of ships. Now, the reason that we talked about a max flow way of solving this is because solving max flow is faster than solving min cost flow. And so if you really had a big problem like this to solve in real life, you would solve it with that max flow application that we talked about earlier because it's considerably faster than solving it with a min cost flow model like the one we have here. So let's just do one more twist on this problem. So suppose that instead of having to complete all of the deliveries, we get a different amount of profit with each delivery. And what we want to do is maximize the profit of our company. So we can do that with min cost flow as well. So let's again begin with the original graph. So this is for maximizing profit. So in maximizing profit, we're not going to have these lower bounds anymore because the shipments are now basically a choice for the company. Maybe they want to take the shipment, maybe they don't. But instead, over here, if this shipment earns $5, what we'll do is we'll have a cost of -5 on it, which means that we earn $5 by doing it. And we can have an upper bound of 1, which means that we can earn $5, but we can only do that for the first time we complete the shipment. It's not like if I send 10 ships, I would earn $50. So a similar thing here. Maybe we make $2 if we complete the shipment, and we have an upper bound of 1 on it, and so forth for the other deliveries. In addition, we can have some costs again for bringing a ship into service. So maybe it costs $10 to bring a ship into service. So we'll just put a cost of 10 on all of these arcs that correspond to bringing a ship into service. And of course, the last thing we have to do is add this backwards arc from T to S. So it would have a cost of 0, an upper bound of infinity, and a lower bound of 0. And so now if we run the problem on this graph with a min cost flow model, it'll try to maximize the profit of this company. So it'll only bring a ship into service if we can use that ship for a sequence of deliveries that ends up making money for the company overall. So that's the basic completion of this tanker scheduling application. You can see that it has lots of little twists we can do to it, as many of the other applications we've looked at in terms of network modeling. So let's look at our next application for today, which is network reliability. In this application, suppose that we have a graph and we have two nodes that want to communicate with each other. So S and T want to communicate. One of the important aspects of this graph, if you think about it as a communication network, is how many different paths exist between S and T that are independent of each other that S and T could communicate on. So imagine that here's S and here's T. And these are some communication relays. So this graph is kind of nice because I have two totally independent paths for S and T to communicate on. So on this path, I have a couple of relays and two different relays on this path. So if one of these relays fails, there's a totally different path for S and T to communicate. On the other hand, if we look at a graph like this, here there is a single relay that can fail to disconnect S and T, but there is not a single edge that can fail to disconnect S and T. So regardless of which edge I take out, there's always going to be a path from S to T that allows S to T to communicate. So you can see that there's some kind of asymmetry between nodes failing and edges failing by looking at this graph. So let's formalize this idea with a couple of definitions. A set of paths is an edge disjoint if no two paths share an edge. And similarly, a set of paths is a node disjoint if no two paths share a node. So in this graph, there's only one node disjoint path maximum that we can find from S to T. So there aren't two paths here that are node disjoint. But in this graph, there are two paths that are node disjoint. On this graph here, there are two paths that are edge disjoint. For example, this path right here and this path right here. They're not node disjoint, but they are edge disjoint. So in terms of these definitions, one thing that's true is that the number of node disjoint paths is always less than or equal to the number of edge disjoint paths. Between two nodes. So you can see that in this example, we had two edge disjoint paths, but only one node disjoint path. And another way to see this is that every node disjoint path is also edge disjoint. Or more specifically, what I mean is every set of node disjoint paths. So every set of node disjoint paths is also edge disjoint. So why is this? It's pretty simple. If I give you two paths and they don't share a node, if these two paths don't share a node, there's no possible way for them to share an edge. So that's why the number of node disjoint paths is always less than or equal to the number of edge disjoint paths. But what we want to do in terms of the network reliability application is if somebody comes along and gives us a network, like this one, say, I want to be able to count the number of edge disjoint paths in the network. So let's just focus on edge disjoint for now. How can we count the number of edge disjoint paths in the network? So to count the number of edge disjoint paths, from S to T, we'll do the following. So give every edge a capacity of 1. And we're going to find the max flow from S to T. And the claim is that the max flow value is actually equal to the number of edge disjoint paths. So why would that be true? So let's see why the max flow value in this graph where every edge has a capacity of 1 actually gives us the number of edge disjoint paths. So imagine that somebody comes along and shows you, let's say, 4 edge disjoint paths. So if I show you these 4 edge disjoint paths, I know for a fact that the max flow value has to be bigger than 4. And that's because I could put 1 unit on each of these separate paths. So we know that the number of edge disjoint paths has to be less than or equal to the max flow value. And that's because we can put 1 unit of flow on each of these paths. But why is the opposite also true? Why is the max flow value also less than or equal to the number of edge disjoint paths? And the reason for this is because we can track each unit of flow from S to T, and no two units share an edge. We know for a fact that no two units share an edge because we made all the edges have a capacity of 1, which means that every edge can only support at most 1 unit. So that tells us that if we take a look at the max flow, we can actually pull out as many edge disjoint paths from that max flow as whatever the max flow value is. So these two things combined tell us that the max flow value is exactly equal to the number of edge disjoint paths. So now if somebody gave me a network and said, I'm going to define the reliability of the network as the number of edge disjoint paths, count the number of edge disjoint paths between S and T, we can just do that using max flow. So here we've been focusing on edge disjoint paths, but how would we do node disjoint paths? So to count node disjoint paths, we're just going to use the node capacity trick. So in other words, we're going to do this trick where if we had a single node, we would just switch it to 2 nodes. And we're going to put a capacity of 1 here. And now when we find the max flow from S to T, that flow is going to be only able to put 1 unit across each node. And so we'll be counting the number of node disjoint paths from S to T. So that completes the network reliability application. You now know how to count the number of edge disjoint paths between 2 nodes, the number of node disjoint paths between 2 nodes. Thanks a lot for listening, and I'll see you all next time.